Okay, folks, let's go ahead and come to order and get moving here. Um, I put up the schedule just so we can see where we are. Today is the 20th. October is 2/3 behind us, pretty close. Um, so we have 3 lectures out of chapter 6, defining entropy and then how to use it in calculations. And then we have our test on Thursday, the 29th. I would anticipate someplace between 10 and 12, maybe 13 fairly short problems where you just ask to calculate one thing. But some of these problems require a couple of equations. So I I never know how a test is going to turn out, but I would suspect that it'll be a little harder than the first one. The first one grades were pretty high, so but that's sometimes instructors think about that as the kiss of death because everybody makes a good grade on the first test, and then they say, "Oh, this course is a piece of cake," and then it comes up and bites them in the behind on the second and third test or final or whatever. So don't you know, if the second test winds up to be as easy as the first test wound up, then maybe you can relax a little bit. I don't know, but I suspect it won't. But I mean, I'm not trying to, bag you, but it's just the material gets a little more in depth and the problems tend to get a little bit harder. So anyway, okay, let's go ahead and get into the presentation here. I did email this out to you, so you have it as per our typical path through this. I'm going to skip the learning outcomes and get right to the first part of the chapter here, which is on introducing an entropy change and doing the entropy balance. Let me move this guy a bit. There we go. Okay, so we're now familiar with mass and energy balances, energy extensive properties. Extensive means if you double the size of the system, you double the amount of the energy, you double the amount of the mass, that sort of thing. Intensive would be like a pressure, a temperature, where you can cut the system in half, but if it's at the same pressure, you don't cut the pressure in half, so just a little bit of review there. So entropy is another very important extensive property that we've referred to in chapter 5, but we've really not defined formally yet. And we will, just as we have done mass and energy balances, and done calculations based on the balance, etc., we will have an entropy balance as well. So it follows along. It's not exactly the same because entropy is a little bit of a different beast, but we'll see that as we go through here. And so like mass and energy, entropy can be transferred across a system boundary. Okay, and what we're going to see, preview of coming attractions, we can transfer entropy with heat, or if you have mass crossing a boundary, that a mass flow coming in or going out, that mass has entropy associated with it, so that will transfer entropy in and out. So you can do it with heat and you can do it with mass transfer. Okay, so this is the inequality of Clausius, or the Clausius inequality, however you want to say that. And this is where we're going to start out. So entropy change, entropy balance concepts are developed using this inequality. So let's just take a minute and look at it, make sure that we've all slept since we talked about this before. So, you've got an integral sign with a little circle on it. So that means you're going to integrate all around the boundary. It's and this is written for a cycle. And remember, a cycle, can have multiple processes. It's like the Rankine cycle is a boiler, a turbine, a condenser, and a pump. Okay, And so a cycle means that we go through all these different processes and the working fluid comes back to the exact same point, and then you start the cycle again and again and again. Okay, so this is defined, Clausius wrote this about a cycle, okay? And so that cyclic integral, we're going to integrate all around the boundary for the entire cycle is what that means. And of course, dq is just a little bit of heat transfer at the point where it enters the system, and we're going to divide it by the absolute temperature. Don't give me any of that Fahrenheit or Celsius crap. I want Kelvin or Rankine, or you're going to get a big red mark, right? Okay. So it's the amount of heat that comes in divided by the temperature on the boundary at the location where it comes in. And so most of the time, in the problems we do, we have one boundary at one temperature, and we know so much heat comes in, and so it's just however much heat came in divided by the temperature. Or it could be a rate of heat coming in. You know, we can do this on rates as well as amounts. We start out with amounts. But this is written in terms of an amount. You don't see a dot, so it's an amount. It's BTUs or it's kilojoules. It's not watts, and it's not BTUs per hour or anything like that unless there's a dot over it, okay? And the sigma turns out to be the entropy production term that we'll define. We're going to get down and define all this stuff. Up to this point, we've kind of danced around it a little bit. Okay, and so as before, if that sigma for the whole cycle turns out to be 0, that tells us there's no irreversibilities within the system. Okay, everything is ideal. If it's greater than 0, then there are irreversibilities like friction and dissipative effects and turbulence and all that good kind of stuff that's always there. And if it's less than 0, it's impossible. It won't happen, or you screwed up the calculation. That's always possible. But in general, if it comes out to be less than 0, then you say impossible. This cannot happen. Yes.
So if Q, does it have the same sign conventions as we've been doing? So when if he exits the control volume, it's negative. If it enters the control volume, it's positive.
I'm sorry. Say that again. I didn't catch the first part of it.
So is Q does it have the same sign convention?
That's correct.
Or negative?
That's correct. That's correct. If the heat comes in, the entropy comes in.
Okay.
If the heat goes out, it's kind of like the cat. If the cat comes in, he brings the entropy. Believe me, if the cat comes in, he brings the entropy with him because he's going to tear something up in a hurry, make a mess. Now, that's correct, and we're going to detail all of that. But that's a really good question. Absolutely. Okay, so this is how we get into the property side of it, defining it as a property. We consider 2 cycles, and they're each composed of internally reversible processes. Okay, so the first cycle is A plus C. So we're going to start at 1, some equilibrium state. We're going to go over to 2, another equilibrium state, and then we're going to come back. Well, we've got 2 different processes that will get us over there and 1 process that will get us back. Okay, and everything is ideal. Everything is internally reversible. Okay. And then we'll just do it here. Okay, so then we write that cyclic integral equals the negative of the production for both processes. So in that top equation over there, we integrate 1 to 2 of delta Q over T for process A, whatever it is, completely arbitrary, but it's internally reversible, so it's ideal. Okay, and then we're going to come back from 2 to 1, so we integrate from 2 to 1 of delta Q over T for process C to get back to 1. So that's a cycle. We go over to 1, we go from 1 to 2, and then we go from 2 back to 1. So we have completed the cycle. And that's equal to the negative of the production term, but since these are internally reversible, that's defined to be 0. So we get to set it equal to 0, okay? And now we're going to do the same thing for the second process. So we're going to go from 1 to 2 by process B, and we're going to go from 2 to 1, again, process C. because apparently we got 2 roads over there and only 1 road back, I don't know. But again, this is all internally reversible, so that's equal to 0, okay? So that's the setup, and then what we're going to do is we're going to subtract the second equation from the first equation. Okay, so we'll just multiply that bottom equation by -1. So we got minus the first integral minus the second integral equals a -0, which doesn't matter. And then we add those 2 equations together, and bingo, what do you get? Well, you see the integral from 2 to 1 by path C, you've got a plus version and a minus version, so they cancel. So you've got the integral from 1 to 2 of delta Q over T by A minus the integral 1 to 2 of delta Q over T B, and then you move that term to the other side of the equation, so it makes it positive, and you get this, okay? Pretty simple. All right, now here's where we start throwing the thermodynamic logic to it. So since A and B are arbitrary, internally reversible processes, linking states 1 and 2, it follows that the value of the integral is independent of the particular internally reversible process and depends only on the end states. So, it only matters where we start, where we finish, and then where we start over here and where we finish back to finish this up. Well, if you remember, and you may well not, I wouldn't blame you if you didn't, but back from chapter 1, that a quantity is a property if and only if its change in value between 2 states is independent of the process linking the 2 states. We conclude that the integral represents the change in some property, at this point unnamed, okay? So logically, this is how all this stuff, I think I mentioned earlier in here, if you go back to the foundation of thermodynamics, it's logic. It's this kind of thing. We define this to be this, therefore this must be this. And then we start writing equations about it, and we get all of the stuff that you study, because at this level we don't go into all of the logic and all of that stuff in terms of all of the definition. You get a little bit of it, but believe me, there's a whole bunch more that undergirds all of thermal. Okay, so ta-da, we call this property entropy and represent it by cap S. If it's cap S, it's the total for the system. If it's a little less, it's entropy per kilogram or per pound mass, whichever system of units you happen to like. So this is a cap S, and you see the integral is a delta cap Q, so that's a total heat transfer sort of thing. So we're doing the entire for the system. So we call this property entropy, represented by S. The entropy change is, now this is for one process, okay? This is not a cycle, okay? This is from 1 to 2, okay? And so the definition of the entropy change here is the integral from 1 to 2 of delta Q over T internally reversible, where the subscript internally reversible signals that the integral is carried out for any internally reversible process linking the states, because once you've done one, you're going to get the same answer no matter how many you do, because it's a property. Okay, so thank you. That's equation 6.2a. Allows the change in entropy between 2 states to be determined by thinking of an internally reversible process between 2 states. But now we're going to generalize it. But since entropy is a property, the value of entropy change applies to any process between the states, internally reversible or not. And see, once you prove it's a property, it's like temperature. If you start, T2 minus T1 is the same value no matter how you get there. If the temperature at T2 is 200, the temperature at T1 is 100, the delta T is 100, and I don't care if you went to the South Pole and back, you still have that same delta T between them because it's a property. So entropy is the same way. even though we go through all of this, derivation stuff in terms of an internally reversible process, it applies to all processes, whether they're internally reversible or not. Did you have a question?
Real quickly, could you go back to slide number 1 and 4?
Oh, I guess if I have to. There you go. Are you good? All right, very good. Those are my favorite kind of questions, the ones that you answer for yourself. No, just teasing. Okay, entropy change is introduced by the integral of that equation 6-2a, for which no accompanying physical picture is given. Still, the aim of chapter 6 is to demonstrate that entropy not only has physical significance, but is essential in thermodynamic analysis. Yeah, absolutely. Okay. So, like we said, entropy is an extensive property, and like any extensive property, the change can be positive, negative, or zero. And now that's for what? A process. Okay, so we just want to be clear when we're speaking of cycles and when we're speaking of individual processes, because there are things true for cycles, like net heat equals net work for a cycle. Okay, that's not, I mean, it depends. And when you're on from one process, you just have to put all of the energy impacts and entropy things associated with that process when you do the analysis. Okay, by inspection units, what you would expect. In SI units, it's kilojoules per degree Kelvin. And in the imperial or US units, it's BTUs per degree Rankine. And you can do specific entropy, the little s, then would be kilojoules per kilogram per degree K, or BTUs per pound per degree R. So just what you would figure. Okay, and if we're working inside the dome, the saturation dome, I was tempted to put a dome up here, but I didn't do it. The specific entropy at some state is, and X is the quality, like we had before. And so what? X is the fraction between 0 and 1. When X is 1, we're what? We're all vapor, right? And when X is 0, we're all liquid. So you see 1 minus X is the fraction that is liquid, and that's times the specific entropy of the saturated liquid, which that's what that little F denotes. And then plus X, the rest of it, the portion that's vapor, times the specific entropy of the gas or the vapor. Those are the subscripts that the authors have chosen to use. And then the second equation is what we typically use. They're the same. They've just done a little bit of algebra, rearranged a little bit. And so the entropy at any state, with a quality, is the entropy of the fluid plus X times the entropy of the vapor minus the entropy of the fluid. Okay? Just it's the same thing that we've done for internal energy and enthalpy and all that. So it works for entropy as well. Okay, and then remember, good review. If we have, say, compressed or subcooled liquid at some pressure and temperature, our first approximation is to assume that whatever property we're looking for, in this case entropy, we evaluate it at the temperature. Don't be evaluating it at the pressure, because all of these things are strongly a function of temperature and weakly a function of pressure. Now, is there a little bit of error in that? Yes, there is. Because when you look it up at the saturated fluid at the temperature, and your pressure is not the saturation pressure. If your pressure is higher than that, then you're a compressed liquid. And so there's it's a bitty error in that. Now, if that pressure is really, really high, then you can go to the compressed liquid tables. But if you go to the compressed liquid tables, I think something like 500 psi is the smallest pressure. And you know, your saturation pressure might be 25 and you're at 27. I mean, come on. You're really, really close to saturation. You're a long ways away from, say, 500. So the thing to do would be to go and just look it up at the temperature and not worry about that little difference. Okay. All right. So but this was the same discussion that we had in chapter 3 for evaluating specific volume, internal energy, and enthalpy. Okay. So we pick up 2 new diagrams. The TS diagram, which is on your left. And so you see temperature and entropy. And, you know, we still got our saturation dome. We still got our critical point. We still got saturated liquid over here on the left and superheated vapor over here on the right. Above this thing is just kind of like stuff. You know, you don't go through this phase transition when you get above the critical point. Lines of constant pressure. Here's a line of constant pressure, and it goes up here. There's a line of constant specific volume, which you don't always see on these diagrams, but they stuck one on this one. Here's a line of constant quality. This shows a quality of 0.2 running up inside the dome. Here's a quality of 0.9 over here close to the saturated vapor. So you can see lines like that. Here's lines of constant enthalpy. I don't know that we've seen those before, how they come down and sweep across out here. So the TS diagram, when we get into the cycles and working with turbines and stuff, we use the TS diagram. After you get used to using TS diagrams, that's my preferred diagram. But you know, it can't be yours because this is probably the first one you've ever seen. You know, so we're just getting to that point. But they're very useful. And then this other turbine people use this a lot in certain specific industries. It's an enthalpy entropy. So this is enthalpy on this scale, and this is entropy over here, and it's called a Mollier diagram. I believe that's right. My French is not really very good. If there's anybody out there who is an expert in French that wants to correct me, feel free. It's fine with me. But I know it's not Mollier. I'm pretty sure of that. I think it's Mollier. Okay. But so he came up with the idea to for this particular diagram. So it's interesting. When you go to these coordinates, look, your critical point is way down here. It's kind of squinched off on the side. You still kind of have a dome, but it's kind of warped and contorted versus all the rest of the domes that we've seen. But anyway, and so you can see lines of constant temperature, lines of constant pressure. Here's a quality line, 0.96, 0.9, that sort of thing. So temperature and pressure lines. So anyway, and you've got much more detailed ones in the tables for the book. At some point, I'll pull one of those up, but we got a lot to cover, so I'm going to keep steaming on here today. We'll do some of that later another day. Okay, so anyway, those are the 2 new diagrams that we get, TS and an HS, or Mollier diagram. Okay, these are some slides. There's a bunch of different relations that get used a lot. And I went ahead and inserted these slides. I put a bunch of slides in this one compared to what the author sent out, because I think this is important stuff. Because you see, there's 2 relations they call the TDS relations. And if you go on into thermo, you use these blasted TDS relations all over the place. Derivations, just, I mean, we use them in this chapter, and from here on, you'll see references in the text to the TDS relations. And so we need to have a good firm foundation on what these are. And they all wind up being in terms of properties. You know, it's relationships amongst properties. Okay. So the TDS equations allow entropy changes to be evaluated from other more readily determined property data. So most of the tables are put together from the more commonly measured properties, and entropy is calculated based on, you know, relations from the TDS and you know, other particular specific situations. The TDS equations are developed by considering a pure, simple, compressible system undergoing an internally reversible process. So just think it as simple as we can. Our little piston cylinder device is a good reference point. And we're going to throw out kinetic potential energy. The energy balance in differential form is, and so we're just going to do little differentials here. So this is, you know, the first law for a closed system, right? We just have rearranged it. We took the work term over on the side with the internal energy. And so we say delta Q, internal reversible, is equal to du plus the differential delta W, and again, internally reversible. We don't need to put internally reversible on du because it's a property and nobody cares if you're a property, right? You don't have to denote it. Okay, so for a simple compressible system, the work mode is volume, expansion, or compression work. And so delta W, internal reversible, is PdV, or just our good old PdV work. Well, we're used to that. And so, yeah, let's go on here. Okay, and then our previous equation, that 6.2b, we just rearrange on a differential form. The delta Q internal reversible is TDS, because what we had ds was delta Q over T. So I can multiply across by T and get delta Q internal reversible is TDS. And then guess what? I'm just going to substitute the PDV and the TDS into this little energy balance equation. Pretty simple. Ta-da! And that's the first of the TDS equations. So TDS is equal to du plus PDV. And it's just, see, everything there is a property. You know, so all of a sudden, see, we start off internally reversible, but if this relationship is true for properties, then it's true for any process, because everything in there is a property. And so that's where the power of this really comes in. We go back to internally reversible to do the derivation, but then once we see it's all properties, we go, oh, wow, man, this is a whole lot better than that. We can use it for irreversible processes, which is everything that actually happens, which is, so it's nice that it turns out that way. Okay, the second TDS equation comes from taking the differential. And, you know, and I like doing this because, you know, you spend a bunch of time in Bruner over there doing derivatives and taking, you know, differentials and all this sort of thing. And so at least we get you over here, and every once in a while, we show you where some of that stuff was important for you to learn. Okay. And so if you take the differential, and that's just the definition of enthalpy, right? Enthalpy, total enthalpy, is total internal energy plus pressure times volume. That's just the definition of it. So we're going to take dH. Well, dH is du plus the differential of the product, PV. And so that's the first times the second plus the second times the first. You remember that. And so dH is du plus PdV plus VdP. And now we're going to rearrange that. And we're going to say du plus PDV is dH minus VdP. Well, there's nothing very high level there, you know, y'all can handle it. And then guess what? We're going to take that first TDS relation. You see its TDS is equal to du plus PDV, but down on the bottom we see du plus PDV is dH minus VdP, so we can substitute it in. And voila, you have the second TDS relation. okay? And so those are in terms of the cap, the total quantities, entropy, enthalpy, and volume, or we can write it on a unit mass basis, with specific entropy, specific internal energy, and specific volume. We get the second equations. Or, God forbid, we should be forced to work in the realm of moles. We thought we escaped Foster Hall intact, never to see those furry little moles again, but lo and behold, they show up. Every once in a while, they raise their ugly head, and here they have again. So that's what the bar means. So that would be the entropy per unit mole, internal energy per unit mole, specific volume per unit mole, etc. So we can do it on a mass basis, we can do it on a mole basis, or we can do it on a total basis. Okay. So those are the TDS relations. And like I said, if you read carefully through the chapters from here on in the thermal book, you'll see those get referred back to pretty frequently. And they're very useful in doing derivations. We're going to use them here in just a minute. Okay, TDS equations. Although TDS equations are derived considering an internal reversible process, an entropy change obtain these equations from the change for any process. So this is where we generalize reversible or irreversible between two equilibrium states of the system. And that's because they only involve properties. Because entropy is a property, the change in entropy between two states is independent of the details of the process linking the states. We've said that about 300 times today. Okay. Okay, so here's just a little example. Consider a change in phase from saturated liquid to saturated vapor at constant temperature and pressure. So we've got our piston cylinder, and we're going to transfer heat into it. The pressure is set by the amount of weight that's on the piston. It's frictionless. We're going to put heat into that thing, and we're going to boil off the liquid until we get all vapor in the container. Well, if you look at that, ds is in general dq over t, but for that process, the work is boundary work, PV, and then you got internal energy. So when you put all that together, it becomes dH. Okay, so ds is dH over t because dH is dq. Okay, and so then when you integrate it or you go all the way across the dome, you see that, well, the entropy change, Sg minus Sf, is the enthalpy change divided by the temperature going across the dome. Well, this is how a relation that's used to generate the steam tables, because it's a whole lot easier to determine enthalpy than it is to go out and try to measure entropy. Go try to measure entropy. You get up early and stay up late trying to do that. So what you do is you figure a relationship for what you're trying to do, and then you go find some more easily measured properties and you calculate. So that's just one little example of that. Okay, now we're going to have special situations. We got ideal gas coming. We've got incompressible substance. If you're working with water and you want to assume it's incompressible, nothing is totally incompressible, but the amount of the error involved in like liquids and stuff like that is usually pretty small. So for most processes, it's okay for a liquid or a solid to assume it's incompressible. Okay, so we start with the TDS relation. TDS is du plus PdV. So once we make the assumption of incompressibility, the specific volume or density is constant, and then the internal energy depends just on temperature. So du, and there is no specific heat at constant volume, there is no specific heat at constant pressure. The subscript goes away and there is just one specific heat, that's C, and it is in general a function of temperature. So du is C of T times dt. Pretty simple. And guess what? dV if you're incompressible, there is no potential volume change. So dV turns out to be 0. And so using that TdS relation, we see that ds then equals C of T dt over the temperature. And if we're willing to assume C is constant, or we take some average value, then we can go ahead and do the integral. Or you can go in the back of your book, or you can go find a big nasty polynomial that gives C as a function of temperature. So you can stick it in there and you can integrate it if you want to punish yourself. But you know, sometimes if you have a wide temperature range, you don't really have a choice. You know, you have to, sometimes you have to do that. Over smaller temperature range, usually some sort of an average works pretty good. And so if you can assume C is constant, then S2 minus S1 integrates into C times the natural log of T2 over T1. Again, using absolute temperatures. Okay, let's do ideal gas here. So guess what? We're going to start with both of the TdS relations. So TdS is du plus pdv, and TdS is dH plus vdp. Ooh, is that have I got a sign error in that? I got a sign error, don't I? Do I have a sign error? No, I don't. Well, hold on, let's go back. I may have a sign error in that one equation. Let's go back. No. Okay. No. Okay. I just want to make sure. Okay. So then we rearrange those and we solve both of them for ds. Okay, so the top one, divide through by t, and ds is du over t plus p over t dv. And the second one is ds is dH over t plus specific volume v over t times dp. And then for an ideal gas, we know that du is Cv of t dt, dH is Cp of t dt, and we know that PV is equal to RT because that's the ideal gas law, okay? So then we do the substitutions. Well, so du, we put in Cv dt over t because the t's in the equation. And then, okay, so let's see, in that first equation, we've got P over T, but if I look at that ideal gas equation, P over T is R over V. Just doing a little solution in my head. And so that P over T, I can put in R over V. And when I do, I get R times dV over V. Oh, well, that's handy. And then the second one, I do likewise, similarly. And so the dH becomes Cp of t dt over t minus. Now see, where's that minus sign come? See, I think I've got a sign error. I've got a sign error. This yeah, I punched these things. I think I've got. I'll clarify this. I think this is a negative sign. Is that not a negative sign? Let's see. So dH, yeah, that's TdS is dH minus VdP. So this guy, dadgummit. I'm sorry. I punched these things the other day. Yeah, this is minus. You know, I was copying and pasting. TdS, dH. Yep, that one's. Nothing like editing your slides on tape for all of the world to be able to watch forever and a day. Let's see. Yeah. I thought there was. Okay, that's okay. Yeah. Say, the one with internal energy is a plus sign. The one with the enthalpy is a minus sign. And see, I finally got it right down here. So this one changes. Well, when I make a mistake, I make it consistently. You got to give me points for that, I guess. There we go. I will send this out again to everyone. I'll verify all that. I'm pretty sure that's correct. Okay. Yeah. Okay. And so then we can integrate to get an equation. So this is for an ideal gas. And so we can then integrate this from 1 to 2 for a finite entropy change. That's all we're going to do is integrate. And so the first one, you know, entropy is a function of temperature and specific volume. And so the first term we have to just indicate. Now, if you're willing to assume CV is constant, then you can pull it out and integrate that into a natural log. On the second term, R is constant. That's the universal gas constant. So you can pull that out. And so the specific volume term integrates into the natural log of V2 over V1. And similarly, in the second one, this is just entropy as a function of temperature and pressure. And so, you know, S2 minus S1, you have the same specific volume integral with dt over t minus r, and the pressure integrates into natural log of P2 over P1. Okay, so that's all good. And then, you know, again, you have to figure out how you're going to handle the specific heat. Most of the time, you know, especially at this level, we just assume it's constant, and then you go ahead and integrate that into Cp times the natural log of T2 over T1. Okay. Or you can look up, you know, again, in the appendices, we have curve fit equations for CV and CP. And then down at the bottom, we see a handy relationship between specific heats. So Cp of T is equal to Cv of T plus R. So the difference between them is the gas constant. And that would be the specific gas constant for the gas that you're working with. Well, and you know, there's a mistake here, dadgummit, because this is the specific gas constant, which is divided by molecular weight, right? Okay. Now we're back to his slides. Hopefully we won't have to edit any of his. Okay. So we put this up there before. This is just in differential form. That's 6.2b. Okay. This indicates that when a closed system undergoing an internally reversible process receives energy by heat transfer, the system experiences an increase in entropy. Okay, so this so if the heat comes in, the sign on the delta Q is plus, and so the sign on the entropy change is positive. Okay. Conversely, when energy is removed by heat transfer, the entropy of the system decreases. From these considerations, we say that entropy transfer accompanies heat transfer. The direction of the entropy transfer is the same as the heat transfer. So the heat comes in, the entropy comes in with it. The heat goes out, the entropy leaves with it. And you just take the amount of the heat divided by the temperature on the boundary where it either came in or went out. Okay. Okay, and internally, in an internally reversible adiabatic process, no, if there's no heat transfer and there's no irreversibilities, entropy can't change. So this is the definition of the isentropic process. This is one of those things. There's a few of these things you need to memorize. When you hear isentropic, you say adiabatic reversible. So when you're sitting around the Thanksgiving table and your grandmother asks you about an isentropic process, you immediately say adiabatic reversible. It just comes out of your mouth. You don't even have to think about it. It just comes out. That's how automatic this needs to be with you. Isentropic, adiabatic reversible. Reversible, no entropy production inside the system. And adiabatic, no heat transfer. And this is for a closed system. And so for a closed system, you don't have any mass coming in or going out. So that's not possible. You don't have any irreversibilities inside the system. So you can't generate anything in there. And you don't have any heat transfer. Guess what? Entropy is constant. It has no choice. Okay.
Did you say adiabatic reversible or reversible?
Reversible.
With the P?
Reversible. Internally reversible.
I think that there's a P.
Well, don't worry. Welcome to my world. I can't hear anything, especially with everybody with these stupid masks on. Pardon my French. Okay, so and that's internally reversible, but isentropic is internally reversible and adiabatic. For a closed system, there's no way entropy can increase. Okay, upon rearrangement of that previous equation, we say delta Q internally reversible is TdS. So then we can integrate from state 1 to state 2. Now, this bullet is kind of independent of the first one. This is just now breaking down. If I have an internally reversible process and there is some heat transfer, I can integrate from 1 to 2 of TdS and calculate what that heat transfer is. Okay, and this gets used quite a bit. So that's this slide. Both of these things you need to study up on and know. And so what that says then, for an internally reversible process, if I plot up TdS, well, that integral is the area under the curve, right, from 1 to 2. So from this, it follows that an energy transfer by heat to a closed system during an internally reversible process is represented by the area under the temperature entropy diagram. So that shows up quite a bit. That's the kind of thing shows up on the FE exam. That's, something like that, something related to that is pretty simple. You can put together a problem that's constant. Say it's constant temperature, and you want to calculate that entropy change, or I'm sorry, that heat transfer. All you got to do is calculate the area of the box, right? If it's constant temperature, it's just, you got the units, you got entropy on one scale and temperature on the other, but so it's pretty practical. Okay, so let's get on to the entropy balance for closed systems. So basically, here we go, S2 minus S1. So for a closed system, this is like your piston cylinder sitting there going through some sort of a process. S2 minus S1, well, we can transfer heat or we can have irreversibility in the system. That's it. So, and so that kind of goes with the definition of isentropic. If S2 minus S1 is 0, guess what? Delta Q needs to be 0, and we need to be internally reversible, which means the sigma, the production term, is 0. So you got to zero out both of them. I guess it's possible that they could cancel out, but that's not the definition of the isentropic process. Okay. Well, subscript B indicates the integrals evaluated at the system boundary. You know that. Okay, and we still have our sigma our production term. The interpretation is the same as for the cycle. So if it's 0, there's no irreversibilities. If it's positive, we have irreversibilities. And if it's less than 0, it is impossible because entropy cannot be destroyed. If that term was negative, then somehow you had a process that was destroying entropy inside that container. And the second law doesn't allow us to do that. Okay, that sigma has a value of 0 when there are no internal irreversibilities, and positive when irreversibilities are present within the system leads to the interpretation that sigma accounts for entropy produced. So he's finally, halfway through chapter 6, he's willing to say that that's entropy production. Well, we've been saying it for a while. Entropy, let's try it. Sigma is entropy production during a process, okay? And so here's the entropy balance in words. And see, this is just putting into words this equation. So change in the amount of entropy contained within the system, and this is right now we're talking about a closed system, during some time interval is the net amount of entropy transferred into the system across the system boundary, accompanying heat transfer during that same time interval, plus any entropy that's produced within the system during that same time interval by friction. Yeah, when I see that production or that sigma, just think friction. Now there's lots of other irreversibilities, but friction works as one very common one. And you can't, if I do this, rub my hand on the table, I generate a little bit of heat. I can't take that heat and convert it back, into energy in my arm or something. It doesn't, it's one way is what we're saying. It only goes one way. And so that is indicated by an increase in the sigma or entropy produced by the system. Okay, little example. 1 kilogram of water vapor contained within a piston cylinder assembly, initially at 5 bar and 400 degrees C, undergoes an adiabatic expansion to a state where pressure is 1 bar, and then we're going to evaluate 2 different temperatures, 1 bar in 200 C and 1 bar in 100 C. Using the entropy balance, determine the nature of the process in each case. So that's going to say, is it reversible, irreversible, or impossible? That's what they mean by determine the nature. Okay, well, as soon as you see that it's adiabatic, you know that the entropy can't go down. Because the only way entropy can go down for this is for heat to be transferred out of that mass, right? Because all you got is heat transfer and production. Well, production is dissipative effects, friction, and it's either, at best it's 0 or it's positive. And so you've only got 2 terms here to work with on the overall entropy change. And the only one that can go down, you can have heat transfer from, that would be a negative entropy transfer out. But if you say it's adiabatic, you eliminate that possibility. So that term is going to be 0, and the other term is 0 or greater. So it can't be negative. It's not going to happen. I mean, as soon as now, if you've got an open system where you've got stuff flowing across the boundary, well, then you got more complication because you got entropy coming in with one flow and going out with another flow. So then the flows have to become part of the balance, but we're doing a control mass where we just have the same molecules, the same particles all the time. Okay, so there's our equation. And guess what? Adiabatic, so there is no delta Q. We set it to 0. So you see S2 minus S1 is the production. That's just solving, you know, putting the math to it. So the mass times the specific entropy at 2 minus 1 is equal to the production. And now he's just going to the tables and looking up. So that's what? That's superheat. I think that's in your superheated vapor table, 5 bar, 400 degrees C. We can go look it up, but that's in your superheat table. So the entropy is 7.7938 kilojoules per kilogram per degree K. And those are the units, you know, that you should get used to. Okay. So then we go to table A4 again. It's still superheated. We're just at what this is, what, 1 bar and what, 200? Yeah, 1 bar, 200 C. We look it up again. Now the entropy is 7.8343. We plug it in, we calculate sigma, and it's a plus 0.0405. So guess what? That's an irreversible process, right? Because we had an entropy increase. And that's what, you know, sigma is positive, irreversibilities are present within the system during expansion A. So life is good. I mean, you know, at least it could happen. Okay, so now we go back to table A4, and now we drop the temperature from 200 to 100. It's still 1 bar. We look up S2 now becomes 7.3614. We plug it in. Oh my God, entropy decreased. Can't happen. Impossible process. Okay, now he's going to drag this out a little bit on the next slide or two, but since sigma is negative, expansion B is impossible. It cannot occur adiabatically. So right there, and so if you look at it, for this to occur, the entropy has to decrease. What would it take for entropy to decrease? Heat would have to be lost from the mass, right? So the only way this can happen is if we have heat lost from that mass to the surroundings. And that's what he's going to talk about here. More about expansion B. You go back to the general equation, and you know, we know sigma is between less than or equal to 0. Sigma cannot be negative. So for expansion B, delta S is negative, then by inspection, the integral must be negative. And so heat transfer from the system must occur in the expansion in order for this to be a possible process. So you better be sucking some heat out of that thing if you're going to start at this point and end at that point. And so this is the kind of stuff the second law gives us. Yes, sir.
So this second term, this integral, that is negative equals negative sigma, right? Is that why the heat transfer needs to be exiting? So or
well,
negative, and so it cancel out to be a positive because those need to balance each other?
Yeah, because I mean, we started out, we said, okay, he said it's adiabatic. So we set the Q term equal to 0. We calculated sigma, and it comes out to be negative. And you go, if I'm going to get between these two states, then I can't have this entropy destruction on this term. So this term comes out to be negative. So the only way I can counteract that, I can make that true, is by having heat lost from this. You see, because this term can be negative. See, this term was positive, right? So we got to transfer enough heat to turn this expression negative. Because say, you know, when you do that calculation, where is that number? Let's go back up. See, right there at the bottom. So if we're going to get between those two states for 1 kilogram, the entropy is going to decrease by 0.4324. It has to. That's what the properties say. Well, up here, look, Well, I mean, in this case, it was positive. So the combination of those terms has to be negative, and the only way that that can happen is for the heat transfer, because the production term at best can be zero, and it won't, in a real process, it won't be zero. It will have a positive contribution. So you have to transfer enough heat so that you can make this true. Okay. Okay, and let's see how we're doing. Okay. So we can also do this on a rate basis. Instead of just having ds, we can differentiate. We can say ds dt, and then the Q terms becomes a heat transfer rate, kilojoules per second, or whatever your time base is, divided by T. And then the sigma becomes a rate of entropy production based on the irreversibilities in the system. So everything just becomes rate. ds dt, time rate of change of entropy of the system. Cap Q dot J divided by T sub J, time rate of entropy transfer through the portion of the boundary whose temperature is Tj. So the rate at which heat's coming across divided by the temperature on the boundary where it crosses. And then sigma dot, time rate of entropy production due to irreversibilities within the system. So it's the same kind of definitions. We just talk about them all being rates instead of amounts. All right, and what do we got here? We've got about 10, we'll go about 10 more minutes, something like that. Okay, so here's another little example. And this is a classic type of problem you get when you get to the second law. An inventor claims that the device shown generates electricity at the rate of 100 kilojoules a second, which is kW, while receiving a heat transfer of energy at a rate of 250 kilojoules a second at a temperature of 500 Kelvin, receiving a second heat transfer at the rate of 350 kilojoules a second at a temperature of 700, and discharging energy by heat transfer at a rate of 500 kilojoules per second at a temperature of 1000. Each heat transfer is positive in the direction of the accompanying arrow. For operation at steady state, evaluate whether this guy has a chance. Are you going to give this guy a patent on this thing? Your reputation is on the line. You got to sign off on it or reject it. So, well, the first thing you do is the energy balance, okay? And so when you plug all that in, you put all the heat transfers in. So what, plus 250 plus 350 minus 500 equals 100 kilojoules a second. And well, that's what he says he's producing. So his energy balance works. Okay, so it's possible in terms of first law. But, we have our second law. See if this guy's trying to, blow some smoke someplace. Okay, so according to the entropy rate balance, so you've got ds dt. So we're going to set that equal to 0 because it's steady state. Nothing's changing with time, so that's equal to 0. And then this is just doing the integration of where the rate of heat coming in divided by the temperature on those 3 different boundaries. So it turns out to be a pretty simple calculation. Is Q dot the rate at 1 divided by the temperature at 1 plus the rate at 2 divided by the temperature at 2, and minus because that one's leaving, so he's going ahead and incorporating that minus sign into that, divided by 3, plus the production term has to equal 0. And that's because it's steady state, okay? So then we plug all the numbers in. So what, he took all of the heat transfers to the other side of the equation. So he puts that minus sign out front, you know, to account for, you know, because this is now on one side and all these are come over here. Or I guess he did it the other way. He left this one over here and took them anyway. So you get this. So just doing the division, you know, this is 0.5, this is 0.5, and this is 0.5. And so this one's plus, plus, and minus, and then I got a minus sign out front, and it says, I don't know about this. I don't think I can sign off on this because we've got a negative rate of production of entropy. So entropy is being destroyed inside his apparatus here, right there. And we know that's not possible. So since sigma is negative, the claim is not in accord with the second law of thermodynamics and is therefore denied. So send him back to his garage. Say, nah, I don't believe this one. You got to bring me another one, you know, and I'll evaluate that one. Okay, that's pretty good. That's, I think, let's see. Let's look at one example problem here, because we can, that's enough for one day on the lecture. Let's see, 24. I thought this one was, this is one of the problems I assigned you. Most of those problems, especially the first, I don't know, 6, 7, 8 are just really simple, you know, look up a property or something like that. So I know it seems like a lot, and you're going to be getting more problems, and you need to stay on top of them. But I think this first group, there's a couple at the end you have to think about a little bit, but most of them are just pretty short and pretty simple. Okay, so we got our friend, a piston cylinder. 1 pound of water contained piston cylinder assembly. Initially, saturated vapor, 1 atmosphere. So we're going to start at saturated vapor, and is condensed at constant pressure to saturated liquid. So we're just going to start over here, and we're going to condense this thing in the piston cylinder. Evaluate the heat transfer in BTUs and the entropy production in BTUs per degree Rankine for water as the system. And then we're going to take an enlarged system consisting of the water and enough of the nearby surroundings that heat transfer occurs only at the ambient temperature of 80 degrees Fahrenheit. So we'll get to that. Assume the state of the nearby surroundings does not change during the process. The water, ignore kinetic potential energy. So let's see, engineering model. Well, here's the picture. So for A, you know, it's just the mass, the control mass is the system. Okay, and there's our diagram. Engineering model, part A, water alone is the system. Part B, the system is enlarged as shown in the schematic. The pressure of the water and thus its temperature remains constant because we're just going across the dome. We know that. Effects of kinetic potential energy are ignored, and the state of the nearby surroundings does not change during the process. Okay. So just looking at this, we're just going from G over here to F. Pretty simple. So let's look at it. So we write the first law, delta U plus kinetic potential energy thrown out is equal to heat transfer minus the work term. And the work is boundary work, which is PdV, and the pressure is constant. So it's P delta V, okay? And so then he's going to solve this for Q, internal energy plus P delta V. And so this is this is delta, this should be delta U, but anyway, so it's the internal energy of the fluid minus the internal energy of the liquid. I'm sorry. Yeah, okay, I guess it flips when it comes over here. He's juggling size. Anyway, this winds up to be, because you've got internal energy and pressure and volume. So this process winds up to be delta H. So these terms all combine to give you the change in enthalpy. Yeah, saying it's negative because we took it to the other side of the equation, because we have to transfer heat out of this thing in order to get it to condense. Okay. So we got 1 pound mass. This is the enthalpy of the liquid, enthalpy of the vapor. And so it comes up 970.32 BTUs have to be transferred out in order to condense this 1 pound of water. Okay, so entropy balance, delta S, integral of delta Q over T on the boundary plus the production term. And so we can juggle this around and we can solve it for the production. So it's delta S minus Q over T. Okay. And so here's our entropy terms. So this is S of the fluid minus S of the vapor minus, and the heat has to be transferred out. So it's a minus 970, and that's the temperature at which this occurs, which comes right out of the steam tables. You just look that up. And they selected this carefully. So it comes out to be 0. Well, if it comes out to be 0, guess what? Process, this is the production term. So this was done internally reversible. Okay? So now for condition B, we have a different situation. This heat transfer from this high temperature out to here is internal to the system. It doesn't cross the system boundary. So the heat transfer for the entropy production is only what crosses the system boundary, and that occurs out here far enough away that it occurs at 80 degrees, not at the temperature in here, because all of this is insulated. We're not allowing any heat transfer from this cylinder now. But we still have to transfer the same amount of heat because we have to condense this stuff. And we got to take out this 970.35 BTUs in order to go from saturated vapor to saturated liquid. So it still has to come out. So for the enlarged system, Q is equal to a negative 970.35 BTUs. The state of the nearby surroundings does not change. So the entropy balance is the delta S for the water minus delta S for the surroundings, which is 0. We got the Q over temperature on the boundary and the production term. Okay, so then sigma equals delta S for the water minus Q divided by the boundary temperature. And so when you run these numbers, we get for this delta S for the water, we get a negative 1.4446, and this is minus the minus because it's lost. But now we have a different temperature, so this combination comes out to be positive. And so we have an entropy increase for the overall process when we include the surroundings, because that heat transfer then occurs at this temperature instead of the high temperature that we used here. Okay. Think about that. Stuff gets, it'll turn you around a little bit. So anyway, we'll continue on in the lecture. Hopefully we get finished next time, and then we can spend sometime next time in the following class just working through some of these problems in class with you. So hope you guys have a great day, and we will cut this off right now, and I'll see you